Okay. So I'm technically a techie. I used to work in software development, and then I decided I wanted to be a mathematician. So now what I do is I go around the country and I try to explain to people how to do mathematics from their point of view. So today I've brought the wonderful buzzword of data. And many of you may be here for data. I will explain data in about 5 seconds and hopefully then go on and talk a bit about mathematics. So I'm going to talk to you today about topological data analysis, how we can use squishy maths to understand data. Okay, so this is the most complicated diagram you're going to see today. It gets simpler from here on in. Great. So as we're all aware, data sets are getting bigger and bigger, and this is the wrong font, but that shouldn't be an issue. And how to get with data, or how to deal with it, is getting harder and harder, as I'm sure we're all aware, plugging behind pandas or Python or something to that effect for hours on end and not really getting much out of it. I remember my days as a software developer and data engineer. It was hard, it was monotonous, and I'm here to kind of try and make it less so. So we need better tools, and better tools, as with a lot of things, comes from mathematics. Mathematics is the language of the universe. You will hear me say that again and again, because I believe it is true. And so I'm going to talk to you today about topological data analysis. And two of those words, hopefully some of you in this room, will kind of understand. Who kind of here knows a little bit about data analysis? We have a show of hands. Great, okay, we've got about half the room, wonderful. Does anyone know anything about topology? We've got a couple of hands. That is more than I usually have. Oh, that's great. That's really nice to hear. Please don't tell me I'm wrong. Warning! I bring a big warning, maths ahead. If you don't like mathematics, you will by the end of this 40 minutes. So don't worry, my job is literally to explain mathematics to you simply. So don't worry if you didn't like maths at school, I'm not going to make you do sums. We're going to look at diagrams and we're going to understand logic. Okay, so let's keep calm and do some maths. Topology. Okay, wonderful. So topology, well, that's probably the first word that we don't really know. What is topology? Squishy maths. I've already used that word, haven't I? Let's explain it a bit better, because squishy maths doesn't really explain what we're doing. So it's a study of physical properties of shapes under kind of physical transformations. So here's a cow, and we can say a cow, when we inflate it, is like a sphere. And many things are like spheres, because you can just inflate them. A balloon, you take a balloon, you blow it up. It's a sphere. You take a cube, imagine you can blow it up. It's a sphere. So topology has a lot of things to do with spheres. So that is one example, but many of the things we're going to see today are going to be moving, and then we're interested in what happens when things move. Okay, so here's another thing we're interested in, things that stay the same. Like Monday, Tuesday, Wednesday, Thursday, Friday, they all end with a Y. That is something that stays the same. And in topology, we're very interested in things that stay the same. And so these properties are what we call invariants. Invariants are things, when you do physical properties, they stay the same. And we'll kind of look at one of them today. We'll be interested in a thing called homology. So here's four. This has gone as well as one can expect, but we will move on. So we have Euler characteristic. I do love technology. Homotopy. Homotopy is all about drawing little paths and curves and then squishing them and seeing what happens. So that's all about lines. Then homology is all about surfaces and shapes and squishing them. And diffeomorphisms are saying things are the same. So this is kind of maybe some of the strongest or the more interesting. And this is the least interesting. So Euler characteristics. An Euler characteristic, if you take a polygon or a shape, vertices minus edges plus faces, that's always 2. That's quite fun, but we're not going to do that today because that's not techie. But what we're going to be doing is we're going to use homology. How are we doing on time? Okay, we're moving very fast. Wonderful. So homology is what we're going to be studying, and we're going to be interested in how we can use homology on data to find things out. Okay, great. Whoa, it moved. Homology. Homology, or homological spaces, are a way to describe shapes via how many holes they have. That's a nice way to describe things. So if we go back, homotopy, that's all to do with lines. This is all to do with, well, this is to do with points, or the characteristic points. Homotopy is all to do with lines. Homology is all to do with like surfaces. So take a banana, cover it in tinfoil. You can work out a homology group from that. Unfortunately, I don't have any fruit on me today in tinfoil, but I could show you via that. And diffeomorphisms, well, they're interested in the whole space. So these are kind of partial, this is full. Okay, great. And homology is all to do with holes. So if you have a donut, or as mathematicians say, a coffee cup, we have one hole. Yes, I got a laugh from that one. I'm in the right space. Great. So if we have a donut, there is one hole in the donut, right through the center. And that will have the same homology group, or the same homology, as everything else that has one hole. So if you take a piece of paper, cut a hole in the middle, that has the same homology as a donut, or a coffee cup, or literally anything else that has one hole. And that's why it's an invariant. It doesn't change. If it has one hole, it doesn't change. Simple. Wonderful. Okay, so they're also based on things called simplicial complexes. Simplicial complexes are fancy triangles, and they're very hard to compute. But we're going to be talking about tech. In tech and computers, we want to be able to compute things. That is the interesting thing that we need. We need to be able to compute things. So the question now is, if we can use homology, A, how do we use it? And B, how do we make it computable? There are two questions that I'm going to answer, hopefully. So how do we compute? Well, there's this thing called the persistent homology. And again, I know at the moment I'm chucking a lot of words at you, and you don't know what most of these words mean. But at some point, yes, I'm aware, I've been doing this for several years now, and this is how I always do it. And everyone goes, oh God, there's words. So don't worry about the words, I'll explain what that means. We know what persistent means. It stays the same, it doesn't go anywhere. Like, I'm persistent staying on this stage. You haven't booed me off yet. And we have homology, which we kind of understand what it's about. So, oh God, okay. It's got more complicated. So, we have point clouds. We have complexes. We have homology and we have barcodes. Some of these words I've already explained, some of them I haven't. And this kind of describes what a persistent homology is in some very abstract way. And what I'm going to do is explain all of these things. And this also explains how we do topological data analysis. And I know that makes no sense to anyone yet, but hopefully in the remaining half an hour, you will have some sort of idea of how to do topological data analysis on things, hopefully in a theoretical way. So persistent homology is what we're interested in, and it's going to be in this kind of diagram, let's call it. So we start with point clouds, that's just going to be data. So we start with data, then we go down to nested complexes. So nested complexes are just a load of triangles. So we take the data, triangulate it. Then we calculate a homology by some way, and then we calculate the barcode. And someone's taking a photograph of me, and I'm used to this. And the barcode is what gives us all of this data. The barcode is what we're interested in. Much like we have barcodes. I need these for my website. Much like when you go and scan kind of things at the shopping kind of place, what's it called? The supermarket. Heavily dyslexic. This is great. So you have the barcode and you shop it at the supermarket, you scan your barcode. What happens is it has information. So this barcode, much like these barcodes, they will give us information about what our data says. So we need to create barcodes from our data and all our topology in order to get our kind of persistence out. And persistence are the things we're interested in. Say, we have a load of data about births and deaths. We want to work out when people kind of are born and when people die, and we're interested in those, and we're interested in the frequency. And we can get that from the barcode. Okay, so let's explain all of these one by one, and then hopefully I can explain links between them. Point clouds. There's a donut, or a torus, or a coffee cup, or whatever you want to call it. There's a load of points. This is our data. So let's take our data set. Whatever it is, I'm sure a lot of you can think in your mind of a data set that you have dealt with. Think of it. Now, think geometrically. What do you think it looks like? Some of you may think of a load of data on a plane. Some of you may think of data in like 3D space, just dotted everywhere. Some of you may have more complicated data. And what we're very much interested in topological data analysis is your more complicated data. Say your data set has like 6 different parameters that leads into it. You can't plot that nicely. That doesn't nicely go into some sort of 3D plot. But topological data analysis is a tool to help us understand that. We can dimensionally reduce using homology groups. Homology groups gives us this 6-dimensional data, and we look at the homology, and it's actually 3 dimensions, or 2 dimensions, or 1 dimension. There's a way to do that. So point clouds are just all of our data in whatever dimension it is. And it doesn't matter what that dimension is, because we can reduce that later. OK, so point clouds. There's my point cloud. Here's a load of data. It doesn't matter what it is. I don't care what it is. We're going to take this as our data. Maybe we can have an x-axis here that says the hours in the day, and then y-axis number of coffee cups drunk. Number of cups of coffee drunk. There we are. So this is just some data. And you can see kind of generically, as we go up the x and y-axis, it kind of gets greater. But that, again, doesn't matter. It's just, for the time, a picture. We can think of data as a point cloud, and so it is a picture. So here's my picture, and we have our point cloud. Let's move forward. Let's make a nested complex. What's that? OK, so simplices. I said that simplexes, or simplices, are just triangles. They are kind of ways to think about fancy triangles. So this is a triangle, this is a triangle, this is a triangle. This is a triangle in 1 dimension. This is a triangle in 2 dimensions. This is a triangle in 3 dimensions. So here, this is called a tetrahedron. And that may take you back to school days. And you can think of this as just a 3D triangle if this went over the screen and it went backwards, and there's a point at the back, and you can't see me pointing, but I can. And you've got the 2-dimensional triangle and 1-dimensional triangle. So we call these delta 1, delta 2, delta 3. There's a delta 4, but delta 4 is more complicated to draw because it's in 4 dimensions. And I may be very smart, but not even I can think about 4 dimensions in my head. So here's our simplices. And what we can form is called a simplicial complex. So if we take these and connect them together, we can create a thing called a simplicial complex. Right. Simplicial complexes, or complexes, are made out of simplices. Because we're interested in computable things, we're only interested in simplicial complexes. So we're only interested in ones where we can make them out of our triangles. OK. So what are nested complexes? Well, they're this thing called a check complex. And they're just formed by putting these triangles together. And this is still nicely computable, because all we have is going to be a load of triangles and a load of lines. And many tech people will say, oh, well, yes, fine, you can compute that, because there will be probably a finite number. Hopefully, we're not dealing with infinite data sets here. So we have a finite number of triangles, lines, or tetrahedrons, or just a finite number, a countable number. And then that will be computable. Okay? So we can model this on a computer somehow. The details, somebody's written code for that. Okay. So we have a complex. A complex is a load of triangles and lines and tetrahedrons that I put together on a point cloud. And a point cloud is just a load of data points that can be thought of as just a picture. Okay. So homology. Let's actually compute them. So let's define a function. What function should it be? It doesn't matter. As long as it's kind of a nice enough function. So we'll worry about distance. Distance is the one that we're usually interested in, because what we've now taken is we've taken data, and now we've gone to a simplicial complex. That is not data anymore. That is a topological thing that we can do stuff with. So let's define a function. We'll use distance. Let's say distance from this point here. Then we can look at the distance of the triangles and the lines, the elements of the simplicial complex. And these are nice numbers. We've only got 1 and 2 here because I took a simple example. So this is 2, so 1, 2 away. Well, this is 1 away because it's touching, 1 away because it's touching, 1 away because it's touching. And what we can do now is we can group or filter them. This is called a filtration. So which ones are 1 away? That one, and that one. Okay, so we have a set of ones that are 1 away. And how many are 2 away? That one. And this is called a filtration. It did say before the fonts got mixed up. Okay, great. So homology is the way to get between these groups. So we have two parts of filtration. We have this bit here, which is our 1 distance away, and we have 2 distance away. And the way to get between them is called the homology group. And there is some function, and I'm hand-waving here because there's a lot of mathematics underneath this, and I thought at this point I would lose everybody. So I'm hand-waving and saying homology is the idea of how to get between the filtration groups. Okay, we don't really need to worry about that. Everyone's coded this already. It's nice to know, but if we don't understand that, you can still understand the rest of the talk, because we still have about 25 minutes left. So, persistent homology. It's a way to use homology to see data through this method. So if we calculate homology groups, then you will have some sort of image of the data, and you want to change things. And when you change things, you want to then look at the homology group again, and things will change. Okay, so that's maybe a bit of a complicated, terse example. So what I've just done is I've done distance. And what we can do is we can pick a different function, and we can get the information that we want. So maybe you're not interested in kind of distance between the points. Maybe, say, we have a load of births and death, and we want to know when the most common kind of death year is. And we have a load of factors, say, time in hospital or something to that effect. And what we will do is we will take that, and we'll define some sort of function, and then you can use the function. I'm being very vague and non-explicit here, because again, there is a lot of stuff that goes underneath this. And you can find the information that we want. Again, there are packages that do this. This is great. You're all probably sitting here going, you've just explained something very complicated to me. I'm not really here for that. How do we use this? I don't quite understand how this is useful. And that's kind of the point. And I want you to now think about why you don't understand. And what we'll do is we'll explain it a different way. Okay, so we have our point clouds, nested complexes, persistent homology, and barcodes. And what I've missed out thus far is how do you change the homology, and what on earth is a barcode? So this is our data, and let's explain it more clearly. I have a line here. So this was part of our original complex. So we take a point, we take a circle of a certain radius. Whatever it is, it doesn't matter at the moment. I've just set it to be this. This purple, all the purple circles will be the same radius. And I look from this point inside the circle, and I go, how many other points can I reach? That one or that one? And I pick one. I pick this one. Okay, great. Okay, we do the same for this one. Draw a circle of a certain radius, the same radius. And we see how many can we reach. Well, I want to draw a triangle here for no apparent reason. I can pick whatever I want. It could be a line. It could be different. And one of the interesting things is if there's a different simplicial complex, then there's a different homology group, and then we get different data coming out. So that is something that we will look at a bit later. So I picked this triangle, but I could have easily picked that, a line here or a line here, and that would give me a different outcome. So let's carry on. Let's move this one up. Same radius. Okay. I don't feel like putting anything here. Let's move this one across. Okay, great. We have a circle of the same radius on this one. Well, let's put a line here. Let's move that one across. Okay, let's put a kind of a 2 simplex here, or a triangle. And I think I'm just about done. So we have circle centered on that one and circle centered on that one. Great. Okay, so we've built our simplicial complex. And again, you may be thinking, okay, great. But now I ask the question is, what if the circle was smaller? What would that simplicial complex look like? It would not be the same. It would be different. Okay? And if it was different, then our homology group would be different. Because the ways to get between, if the simplicial complex is different, then the ways to get between the kind of the filtration will be different. Or if the circle was larger, then again it would be different. Okay, then we could create different complexes and different homologies. And we would see different persistent features. So the things that will come out of our homology will be different. And if there is a feature that is in all of them, it would be persistent. It would be there, and it would be there in all of them. So that would be something that would be invariant on the homology groups. And if you have something invariant on the homology groups, then it must be important. And you can link that back to your original data, and that will be something that the data is telling you. That will be a feature of the data. Okay? And how do we actually see something from these homology groups? As I said, via barcodes. So barcodes are intervals that track the lifetime of these features. So many of you will now be thinking, lifetime? Things will appear and disappear. Yes. Topological data analysis can see beyond the greater trends. Topological data analysis can give you shorter little barcodes for features that only exist for a certain amount of time in your data. Say if you've got a time kind of interval, say you've got data over 10 years. Maybe for a couple of years, a feature will be there, but only for a couple of years. And topological data analysis can tell you that, because it is both a local way to analyze data and a global way. Okay, so here's an example. Here's some data. So it goes up and down. And what I've said here is I've set up something to say, okay, I'm interested when there is a massive turning point in the data. Say this is over time, and this is sales. And this is kind of some sort of continuous. I know it's continuous. Data isn't usually continuous, but it kind of shows my point. So over time, there will be some sort of change. And I'm interested in kind of turning points in my data. So I run an algorithm. It gives me a barcode. This is what a barcode looks like. And I have a diagram. A diagram will show me either the start or the end. And it will be very much symmetric. So it'll be symmetric around this line here. So I don't need to plot the other bits. So here we have 3 points of data. This will tell us when 3 turning points are. And it'll be symmetric on the other side. And so there is, well, it's the death and birth one. That's the example I was kind of alluding to earlier. Okay, here's another example. And we've got about 20 minutes, so I've run a bit under, but that's fine. So we have some more data here. So here's a point cloud. Here's some data. Then what we've done here is we've taken our circles, and we look here, and no other circles are touching some data apart from that one, but I chose not to put a kind of line there. And here's the barcode. That shows some data. And then we get them a bit bigger, and we can kind of create a simplex filled with lines, and then we have some more data. And we look at the difference between the two. And we get a new blue barcode. This tells me the difference. Usually in topological data analysis, we have some sort of red, which is the current, and blue talks about the difference. And as we get bigger and bigger circles, what we see is we have this kind of, this red line here is persistent. It is seen throughout the data, and so what we have is we have a persistent piece of information which tells us data about our kind of data set. So this blue one here, that kind of will show this big red one, and the shorter one, that will show something else that's in the data. Okay, so hopefully that's given a quick overview of what it is. And I'm going to kind of talk a bit wavy about how we actually do this. So a lot of people have already implemented a lot of algorithms to do with this, and a lot of people are using this in their everyday work. So if you're interested in applications, I will talk a little bit about that at the end. There's a whole database of people that are using this. People use it for things like healthcare. People use this in engineering. It's mostly a way that we can take high impact data that's of high dimension, and then we can do some sort of topology on it, and it gives us better ideas of what to do rather than kind of classical techniques. Mainly because classical techniques are not very good at kind of high dimension data sets. So this is some way that we can not think about the data, because topology doesn't really care how many dimensions your data has. All it cares about is the connections between it. And many kind of current algorithms are very interested in the dimension because you're connecting up all the different nodes, and if you've got more data, then you've got more nodes to connect. and all these kind of algorithms get very, very complicated very quickly. Okay, so what we've just seen is called the mapper algorithm, and it's this general idea that was originally introduced by the original people who worked on topological data analysis. And they put together this mapper algorithm as a general way to deal with data using topology. Okay, this is a general approach to topological data analysis problems. You take your data, you point cloud it, then you calculate your homologies using known packages, and then you get a barcode out. Okay, so as I kind of draw to the end, I'm running a bit quick, but that's fine. Why TDA? So it's more sensitive to fluctuations. It isn't just noise. So in many kind of data applications, what we see is people sitting there and they look at their data and they go, okay, I've seen a pattern. That may just be noise. Topological data analysis can prove whether it is noise or not. Because if it isn't noise, then you'll get something in your barcode. If it is noise, then you won't. You can see kind of death and, You can see kind of death and birth of patterns. So if you have patterns, then you can see them arriving and disappearing. More global algorithms won't see that. More global algorithms will kind of show you something to the effect of, okay, this is generic. This is a generic idea of what's going on. In topological data analysis, you can kind of time step through, look at your barcode, and it'll tell you the death and birth. And this is one for me. It uses really cool maths. I think it uses some cool bits of maths that we don't see enough in kind of major industrial applications. And if it's there, we might as well use it. And I think that is that, apart from this one. So if you're really interested in how you can use this for yourself, there is a database of papers and kind of uses called Donut. And they will show you how they used it and kind of what you can do with topological data analysis. I think, thank you very much.